So, as you will notice, you're being filmed today. So, this is part of our faculty learning program. So, that German and I, German is also observing today as well. It'll be essentially the back of your heads. So, for the most part, you don't have to worry about being on film. They'll kind of follow me around. But yeah, this is all just part of a Berkeley program that we're in to assess how we're teaching. That's why I'm all in the get up today. Good, huh? Not bad, huh? All right. So a couple things to quickly go over. First off, I want to say great job on the field trip. That was awesome up there. I actually wasn't expecting a lot out of that field trip as far as the location, the fact that we're looking at Copeland Creek a lot. But that turned out to be a great field trip, and I feel like you guys took a lot out of it. Caesar Chavez Day, no class on Thursday. Okay, so no lab, no class. Lake Berryessa field trip. So I know we talked about that on May 5th. I'm going to change that to April 28th. The reason for that being is that I want May 5th is the last class period we have before your lab final. I want to use that lab final to, or that class period to prep you. So we'll get all the trays of rocks out again. We'll have everything ready for essentially discussions about field trips, because the lab final will cover everything that's in class and in the field. Okay, so I want that to be our last little chance for a review session. Yep. So that'll be April 28th is Lake Berryessa now instead of May 5th. Still the same window class period. I expect that one, just so you know, those of you that work and stuff like that, and sometimes we get out of here on time, please make sure that you don't plan anything for that day. Lake Berryessa is like an hour and a half away. So hour and a half there, hour and a half back. That's 3 hours. That gives us about 2 hours to be in the field, okay? So make sure to plan on that day being the full day. As you all are getting aware, I can just talk about this quickly. CFA has released their fact-finding report. We might not have a agreement before the strike date. So I'm just starting to prepare us in case the strike happens, okay? If the strike happens, we're going to lose the 14th and the 18th. The unfortunate thing is the 14th was supposed to be Point Reyes. So we might lose Point Reyes, but that's all right. And then also the 18th was going to be our field trip lecture for our big field trip down to Fort Hunter Liggett. And if we lose that, we're going to have to push a couple things forward, or we can do a lot of that prep that first night when we get down there in the field. I'll just essentially make a lecture for when we get into the field. We'll just project it on like the side of the van or something like that. Okay, so that's pretty much logistics that we had to take care of. Let's get into carbonate depositional environments. But before we do, hey, Socratic quiz. All right. Where is it? I don't know if it was there. 2 seconds, guys. Yeah, I might have not put it in there. Give me 2 seconds here, guys. Quizzes. Choose. Manage quizzes. Dashboard. Start a quiz. Comments 2. Okay. You guys hated this question last time, so I'm going to start out with this time. This is the one that almost killed you guys in the space race. Except for Tyler. I think you got it. Saved the extra point. Oh, the screen's going to do this again today, huh? All right, try to see what happens. So again, please take your time with these. I highly encourage, again, talking to your partner, the person next to you about it. Try to get the questions right. 21, 23. You guys are all, wait. No, we're missing Rich today. I was going to say we have everybody here today.
Almost.
Almost. She ruined it. You can tell her she's ruined our perfect attendance day. Take a second on question number 5. Just think about what happens through time post-depositionally. Okay, after things are deposited, what might happen to it? Let's just beat us. No, I know it's good. It's just straight.
Resources.
Where'd this come from? This last year's?
That's geology. No, it's we're using our resources.
Maybe one or two, about 2 more minutes. Looks like a lot of people are still answering question 5, so. They don't have one here, so I just have to press video. Yeah, usually you just press, yeah, mute and this goes. So I just hit video and then go back to computer. It works. Not ideal, but it works. Yeah, this classroom doesn't have the mute button. So. One more minute. Okay, it looks like most people have finished. I'm interested to see what somebody wrote for their number 5. Starts with Owen, so. This is the worst part. Okay, we've been dealing with this all year, but we'll get there. Good? Yeah. Okay, for now, it might flicker a little bit. It's gonna happen. Okay. So, mudstone, waxstone, packstone, grainstone, and boundstone are part of which classification scheme? Back row. Done. Yep. We the folk class. What's the only name we use from the folk classification scheme that I want you guys to use? Versus this one right here. What's another name for mudstone? Oh, close. Siltstone's a clastic depositional thing. Claystone's also clastic. Siltstone, claystone, mudstone, micrite. Okay, micrite. Yeah, just because the reason we don't say mudstone, or I don't like the use of the term mudstone, is because it can easily be connotated with a siliciclastic depositional environment. Okay. So how'd we do? Good, 100%. Well done. Okay, grain-supported carbonate that contains no mud, 0 mud, and is grain-supported. Front row, what do you guys think?
Greenstone.
Grainstone, how'd we do? Good. Okay, yep, again, with packstone and waxstone. So that is grain-supported, or not grain-supported, so that's the difference with waxstone. Packstone is grain-supported, but it does contain some mud. Okay? Our modern ocean favors organisms made of aragonite or calcite, third row? Aragonite. We have aragonitic seas right now. Okay, does that mean there's no calcite producing organisms? No. Okay, it just means it favors it. In the past, we had a higher calcium-magnesium ratio, which favored more calcium-rich seas. Now, we have a little more of what is just aragonitic seas. Okay, a lot of the organisms tend to build their shells out of aragonite versus calcite. Again, this is something that's happened a lot through the past, but some organisms will switch what they're using to build their shell out of, and some organisms will just stay with the same thing the whole time and just make do. Okay, some organisms will really struggle with the switch. How do we do? All right. So that might be on a test. Okay, in a lagoon, you are more likely to find blank. In a shoal, you're more likely to find blank. Row 2. So we think in a lagoon, are you more likely to find paloids or ooids? Paloids, okay? And then on the shoal, you're obviously more likely to find ooids then. Why is that? Why in a lagoon are we going to find that paloid versus the ooid? What's the difference in, go ahead. A lot more, exactly. So the big difference between those two is somewhat their size, right? And a little bit of their composition. But essentially size is a big part of that. In a lagoon, you have quiet water environment versus on a shoal, you're heavily being beaten by waves and stuff like that and currents, okay? So in a lagoon, you have a little more of a protected environment. You're allowed to settle out muds and things like fecal pellets and stuff like that, okay? Good. Okay, why is dolostone quite rare from recent geologic deposits and quite abundant in ancient deposits? Anybody? Why do we find so much dolomite in ancient deposits? And what's this? All right, I'm going to find there's a curious answer there somewhere. Anyone? What happens? Yeah, go ahead.
Dolomite takes ancient limestone, changes into dolomite. So
Absolutely.
You have to have the limestone first before it becomes.
Do you remember what's the big mineral that's in dolomite that's not as abundant in limestone?
Magnesium.
Magnesium. Okay, magnesium-rich waters that flow through the groundwater convert things like limestone and calcite to dolostone and dolomite. Okay, so essentially meteoric waters that carry a lot of magnesium in them convert ancient deposits. This is why also dolomite is a lot harder. It's easier to preserve. If you ever drop acid on it, you have to scrape it first to get it to fizz. That is kind of a product of that calcium-magnesium ratio. If you guys remember that from Geology 102, having to scrape the dolomite first before you put acid on it. You kind of create a powder first because there's not as much calcium to play with. All right, and last one. Oh wait, I want to see, what did somebody say? Owen, you're awesome, but I honestly don't know the answer. Great. Okay. Starfish, sand dollars, and crinoids are part of this group. Again, anyone? Echinoderms, good. What makes the echinoderms special? What do they have that is
Radial symmetry.
radial symmetry? Yeah, relatively characteristic to the echinoderms. Radial symmetry, okay? Peripera, if you remember, pore space, peripera, okay? Mollusks are more like bivalves, and bryozoans are kind of those branched-like tree things with holes in them again. Okay. Finish it up, get the report, download it. So, Just to kind of wrap up this last little thoughts of last week, I want to make sure that we're familiar with the Dunham classification. Again, the basic idea behind this is that we have more matrix. All right, essentially the amount of matrix versus grains. Okay, so in both of these, they're mud supported or matrix supported. And both of these, in packstone and grainstone, they're grain supported. All right, waxstone has at least 10% grains, and a grainstone has no mud. And then think of a boundstone. Again, there are a lot more names. Okay, bindstone, rootstone. There's a lot more names that we can classify this category into. But think of it like the reef itself, not the broken fragments of the reef. This is something that's in place and has stuff filled in around it. Okay, so I just want to make sure we're clear on these classifications. You guys will be using them a lot in the lab. I don't think, as of right now, I will make you guys further classify into things like bindstone, rootstone, all those other classifications. But just know that they exist, that we can break up that final category into a bunch of other categories. And also, as we mentioned before, we also usually want to identify the fossil that's associated with it. That fossil can tell us something about that depositional environment, what it's composed of, if it likes moving water, if it likes quiet water, and so on. Okay? So we've pretty much figured out how to classify these things last time. In last class, we spent a lot of time on what are the names and how are they formed. Okay? Now we want to figure out where deposition occurs. So we're going to look at, we're going to focus a little bit less on the non-skeletal grains, right? Things like ooids, pellets, all those. We focus a little bit more on the skeletal grains, but for the most part, we're just going to overview what is the depositional environment of carbonates. Okay? So again, this is kind of more of a diagram showing one of the non-skeletal fragments that we've seen before. And this is a cross-section from Alberta showing where you have grainstones, where you have waxstones, where you have packstones, where you have these different facies, if you will, of these rocks. Now, where do these actually occur in the depositional environment? Now, for the most part, our carbonate shelves are located in low latitude, okay? So usually between about 30 degrees north and 30 degrees south. They're shallow, they're tropical to subtropical seas, and they have relatively little terrigenous siliciclastic sediment. You guys know what I mean by terrigenous siliciclastic sediment? Siliciclastic sediment that's coming off of the continents, okay? So siliciclastic sediment, really, okay? This happens, for the most part, in the upper part of the water column. Okay, this is meters on the left-hand side, and on the top you have rate of calcium carbonate production per unit area. Those of you that came to Tessa Hill's talk last Thursday, she talked a lot about putting carbon dioxide into the seawater and essentially how these organisms use that to build their shells. You put too much CO2 in the water, it creates a lot more carbonic acid and bicarbonate and less availability of calcium carbonate to build shells. So the same concept in the upper part, if they don't have photosynthesis to work with, if organisms don't have photosynthesis to work with, they build slower and they can't build as fast and they can't build as large and they can't build as big of organisms. Yep?
Sorry, so you said siliclastic sediment?
Siliciclastic, yep. So just think of it as silica, like quartz. So plastic sediment. Sediment that's coming off of a continent, really. Just like everything we've talked about for the most part of this class before, carbonates. All that kind of sediment. You just pretty much have, for the most part, we've gone through carbonates and siliciclastics so far. We'll get into evaporites, and we'll talk a little bit about evaporites in next week. Okay, but for the most part, that's all the other type of sediments we talked about. So as you can see, you have a really high production rate in the top 10 meters, the top 30 feet, where light can get through that water column. You can get these things, especially like red algae and Halmeta is type of kind of algal bloom as well. So you can get these things down to almost 300 feet. But for the most part, this stuff is happening in the upper part of the water column, in the top 30 feet, or in the upper couple hundred feet. Okay? Now, what controls this in a more holistic sense? We're going to go through each one of these in more detail as we go through the class, but this is essentially what I want you guys to kind of take away from this, is what are the factors that control the development of carbonate production, okay? So bank geometry, we'll talk about ramps and non-rim shelves, pyric platforms and isolated platforms. Okay. Turbulence. Okay, so how turbulent is the water? Does the water have things like waves crashing through it or currents crashing through it? Again, we talked, Tessa Hill's talking about the currents along western North America. We'll talk a little bit about that and how it affects the organisms that can survive there. Clastic sedimentation. Again, what kind of influence does this have on the organisms that can survive in an area where there's no clastic sedimentation, not a lot of rivers dumping into the ocean, versus an area that has a lot of rivers dumping into the ocean, especially a lot of sediment. What is the biologic influence? Again, how do these organisms actually create reefs, build reefs, versus something like, mollusks just along the shoreline? And then sea level rise and fall. How does the rise and fall of sea level throughout our geologic history affect what type of carbonate platforms that we might create and what kind of organisms might exist? So I want to go over two things that we're not going to really focus on, but that exist. Okay, this is just because they aren't the bulk of the geologic record, and if we had a full-on carbonates class, we would spend about a week on these type of deposits. But high latitude carbonates. Again, we talk about most of the carbonate factory being within the mid latitudes, right? Within the middle of our near the equator, within 30 degrees of the equator. But cold water carbonates do exist. A lot of times they're things like shell remains. So if you have a bunch of mollusks, brachiopods, bryozoans, those kind of things, not so much bryozoans. But essentially, as those things get reworked by wave processes, these can turn into shell hashes and remain as a carbonate. Okay, there are also are cold water patch reefs and things associated with upwelling, but we will not make this a focus of today. There are also our terrestrial carbonates. Okay, now these things can easily be mistaken or thought of as evaporites. Okay, think about Mammoth Hot Springs or Crystal Geysers, the cold spring, one of the rare cold spring geysers of the world that builds up CO2 and erupts. Now, the reason these things aren't necessarily evaporites is because they have a biologic component to them. They are being built up like Mono Lake, the tufas in Mono Lake in California. These things are being built up by organisms, and they are carbonate-secreting organisms. Okay, so again, they make up some of our geologic record, but not a huge percentage of it. And since we only have one day to really go through carbonate environments, we are going to focus on the marine realm, the shallow water, warm marine realm. So, the geometry, okay? And we'll spend a good bit of today talking about each one of these geometries. The geometry controls if it is essentially a restricted or unrestricted environment. So, in something like a carbonate platform, if we look at a rimmed platform or an unrimmed platform, all right, what this means is that there's actually a large hump out here of maybe a reef or a shoal that is restricting that environment behind here. Sometimes we'll talk about this as being the carbonate factory. There's a lot of carbonates that essentially build up in that region right behind the reefs. But this really affects, what's happening. Again, something coming along here, waves are crashing and hitting the actual fringe reef, that rim. Whereas in an open shelf environment, a non-rimmed shelf, those waves are coming and actually crashing along the shoreline. That's going to heavily influence what type of deposit you have, because you have either a high energy environment near your shoreline or a relatively low energy environment near your shoreline. So the unrimmed versus rimmed platform is a big one. And then we'll talk a little bit about the isolated platform too as well and how that affects. We'll start out with the rimmed shelves. Okay, so in a rimmed shelf, again, you've built up either a shoal, in this case a shoal out here, or some type of reef on the front rimmed margin of your continental shelf. Okay, what this does is restricts the platform interior. So again, the scales of these, usually that reef or that shoal is usually tens of kilometers, 0 to tens of kilometers. Yet the platform interior can be quite large. You can have a big carbonate platform inside of that. And also, as you go out to your slope or basin, so as you get out to the outer shelf and out into your slope, this can extend for quite a ways as well. In a lot of modern environments, this is a relatively narrow window before it reaches the abyssal plain. So this is going to heavily affect essentially what type of deposits, lime, sands, and muds in a restricted environment. Off the shelf, you have a steep slope afterwards. This is still allowed to carry things like turbidites down. Okay, we think of turbidites being a siliciclastic depositional environment. Turbidites can happen along a carbonate reef as well. You still have large production of sediment, and these things still can get on a slope and fail and wash down into the deep basin. Okay? So if we look at like a basin and slope deposit, as we get out there, a lot of times you're dominated by pelagic sediments, okay, those deep water sediments, just raining out sediments. But you also might get some turbidites and debris flows. Along the platform margin, okay, where you actually have a shoal, you might have, again, sand shoals. So sand shoals are things going to be like ooids and non-skeletal fragments, or you might have a reef restricting that environment, okay? And then in the platform interior, so we'll talk about Pyrex seas. In that lagoon or bay, you essentially might have a tidal flat, so you're going to have a very, very muddy or less class inside of that lagoon environment. Kind of depicting it again from the side and from the top here. So on a ribbed carbonate shelf, interior, you might have some grainstones and pack stones, again, as those waves are crashing against that reef, washing that sediment into the lagoon. Initially, you might have some grainstones. As you get farther back away from that reef, you'll have maybe more mudstones and wax stones. The reef itself will turn into something like a bound stone, again, so the reef is staying strong, and all of its fragments are constantly breaking off and shedding either way. And then along the fore reef, if you will, so whenever we talk about fore and back, so fore reef would be oceanward of the reef, look like foreland basin, back arc basin, all those kind of terms we've already kind of talked about a little bit. But essentially, back means behind, landward on the land side, and fore means out in front of, okay? So the fore reef slope, again, they talk about root stones. That's just kind of like a big version of a grainstone, but essentially a lot of grainstones and pack stones are also going to be in this type of environment. Then as you get out into the basin, the carbonate mudstones. So looking at it in a cross section, as this might build, you might have that reef complex kind of build out as sea level rises. The lagoon might expand. But essentially, looking at a cross-sectional view, you'd see something very similar to that. Mudstones in the interior with grainstones and wax stones. As you have the lagoon, or as you have that reef build, bound stones, and then interior, some kind of sandstone. So looking at a real-world example of this, one of the best places to do this, I'm going to show a lot of Google Earth images. You guys want? I can't have the lights off. We're filming. So there's a lot of Google Earth images here, so bear with me as far as some of the dark blues. I know they don't show up that great with this much light. So this is the South Florida Bay. This is a good example of a rimmed shelf, okay? So out here, we have very much minimal carbonate and mud deposition, okay? Less than 50%, or greater than 50% mud. Yep, that is greater than 50% mud. And even higher than that. So, or you just have just pure pelagic sediment raining out down there, okay? So you might get some turbidite deposits that are bringing something out there. So what type of deposit would we call that if it's dominated by mud? Actually, let me say that right there. So what is the other name that we talked about this already, but what is the other name then if it's dominated by pure mud? Micrite or mudstone, okay? So we have mudstone and micrite, again, in these two depositional environments. In a tidal flat, so up in this area, up here, we also are dominated by mud, and this is the tidal flat. This is the Everglades. This is the southern tip of the Everglades. They have a bit of a tidal influence. Okay, so the tides are coming up, washing into these areas, and then coming out. But for the most part, it's just mud, a lot of mud deposition in that area. If we zoom in near Isla Morada, we can kind of see that this is about a 20-meter depth of the edge of the shelf, or at the edge of the essentially reef and shoal complex. Just interior of that, we deposit a lot of gravel. So if we have a lot of gravel, lax muds, grain supported, what's our name? It's grainstone, okay? As we get farther in, we have a lot of sand, 0 to 10% mud. This is still pretty much grain supported, but now you have some mud. What's our name? Packstone, there you go, packstones, okay? And as we get even farther interior from the shelf into the lagoons on either side of the islands, essentially you have sand with 0 to 50% mud. If you think about this, let's just say there's 10% skeletal fragments. What's the name? Mudstone. Or no, Waxstone. There you go, waxstone. Okay, so you just kind of see how in a modern environment these features can show up. So looking into the inner lagoon area, we have this protected environment that we have some skeletal fragments. Again, there's some stuff being pushed off of the back of the reef, but a lot of this is being deposited in this region. What do we call that? That non-skeletal reef. Go ahead, just think about it for a second. Talk maybe with your neighbor. What's the name of that? What is this little guy that dominates deposition within a lagoon? Fine-grained. Okay, what is it? Yeah, pellets and pelloids. Again, these are little just clumps of mud, but what creates the little clumps? Yeah, fish poop. Okay, so it's fecal pellets. All right, it's not always fecal pellets, but a big portion of this is some kind of essentially fecal pellet deposition from the organisms. Okay, so like relatively quiet water deposition. Again, you can get waxstones and packstones that get pushed into there as you have essentially the tides come in and out of the bay. They'll essentially carry sediment off the reef into the lagoon. But as you get into the heart of the lagoon, you get a lot of pelloid deposition. As you move farther up, as we get near the Everglades, and we get farther up into the South Florida Bay, we start to get on tidal flats. We talk about tidal flats a lot with the Bay of Fundy and so on, because you have such a huge tidal range, but that's a siliciclastic depositional environment. This is more carbonate depositional environment. So you don't have a lot of energy here, so you do build up these kind of almost algal mats. All right, if you see in this image here, this is actually just a formation of these kind of algal mats. Some like kind of green algae will form. These things have water rushing in on them, sitting on them for the day, and then leaving. If you ever walk out onto, not so much the beaches around here, because they just don't tend to favor that algal mat formation, but I guess if you go into Bodega Bay, and if you're ever driving out on Duran Beach and you look into the right-hand side, there's a proper tidal flat there. Again, mostly muds are going to kind of dominate that environment, if you will, carbonaceous ooze. So essentially organisms that have secreted out some kind of carbonate. But a lot of kind of algae production happens in those tidal flats. Okay? And what's the name of that clast? So this is a clast that forms as you are on the tidal flat and you've gone from a relatively low energy environment, and then maybe you have a hurricane or a storm come in. You're going to think of one name that we talked about a lot in siliciclastics. That's a storm deposit. This isn't that name. I'm just looking for the name of this little fragment that gets ripped up and redeposited in this environment commonly. Go ahead and talk with your partner. What do you think the name of it is? These are the chunks of mud, if you will, get pulled up as you have some kind of storm that breaches past these barriers and still produces big waves in an otherwise quiet environment. All right, back to rows. Anybody know it? Yes, interclass. Okay, interclass. Okay, so interclass are essentially, if you think about it, these things are subaerial for a long period of time. Okay, they're allowed to partially lithify. They're made of lime mud. Okay, they start to actually solidify in place. Then you have a high energy environment come through, and it can actually break these little chunks out, bring them out a little bit into the lagoon sometimes. But a lot of times you get a lot of interclass deposition in an environment like this. Okay, so you get these kind of clasts of previously partially lithified sediments that are broken up and next to each other. Think of it like the carbonate version of a conglomerate. Okay. All right. As we get into another geometry, a slope geometry. Okay, this is an unrimmed shelf. Okay, you can also kind of think of this as a ramp sometimes these transitions aren't very far off from one another. In this case, you actually, the basic idea between a shelf and a ramp is that on a ramp, you're essentially going to go from continent to ocean in a relatively smooth transition. Okay? That's usually pretty hard to do. As we'll look at here, as we go into this unrimmed shelf, you usually have some kind of shelf break. Okay? So now we change up our stacking pattern a little bit of how actually these carbonates are laid out. We no longer have our high energy environment out near the front end. Okay? It's back near the foreshore. Okay, so in a non-rimmed carbonate shelf, the inner shelf is a grainstone or a packstone. Okay, grainstones. Whenever you think of a grainstone, think of relatively high energy. It's cleaning out all the mud out of that environment. Okay, so the inner shelf is kind of a grainstone, packstone. Our outer shelf is more of a packstone, waxstone again. So this is more like a regular shelf geometry, if you guys thought of as far as sandstones near the shore and mudstones as you kind of go off of shore. So redeposited limestone, and as you get into the deep water, you get more of a carbonate mudstone. So if we look at this area, kind of zoomed in off the backside of the slope, it looks very similar to what we almost see almost up the coast of California. Another coast, you have that steep slope going down to the basin from the actual carbonate shelf. Okay, so up here, you're on a shelf. Down here, you're on a slope. Then you're down in the abyssal plain. It's a very similar geometry to what we have in a siliciclastic depositional environment. Lastly, kind of just looking at the depositional environment of the ramp. So again, high energy up here, shoals or grainstones. As we get into the mid-shelf, again, these are still there's still corals and stuff like that growing out there. These aren't barren seas. These aren't sand shoals. These aren't just like these big kind of moving waves of sand out there. There's a lot of life that exists along these carbonate ramps. Sometimes they'll actually have these little patch reefs or buildups that are forming outside on the actual shelf. But for the most part, the geometry is just heading out to the basin. So you pretty much go from coarse grain, high energy, slowly transitioning out to fine grain and low energy. Okay. So these kind of shelves, unrimmed shelves and slopes, dominate the margins of our continents right now. But one thing we kind of lack these days that was very common in the past is a really, really high sea level. Okay, so we have high sea level right now, but we still have a lot of water locked up on glaciers. Our spreading ridges aren't moving as fast, so our sea level isn't as high. And so right now, our modern isn't a perfect indication of what's happened in the past. In the past, we had a lot of these Epiric seas. Okay, these Epiric seas were big, epicontinental, big, shallow seas that cover huge areas of our landmass. So this is during the Ordovician high stand, Great Ordovician high stand, if you will. And you can see that there's very little of North America that is actually exposed. And we have these huge seas that are actually coming up onto land and covering the bulk of our landmass. Okay? There are some modern examples that are close, essentially because we had such a large sea level rise at the end of the last ice age. So the height of the last ice age, if you will, is about 20,000 years ago. By about 15,000 years ago, we're reaching a point of relatively rapid melting of our glaciers. And by about 5,000 years ago, sea levels have approached their current level. Okay, so from about 15,000 to 5,000, during that 10,000 year interval, we raise our sea level almost 300 feet. Okay, so during that high rise in sea level, the Sunda Sea in the South China Sea, this area has somewhat become that since the Pleistocene. Okay, this area was exposed during the last ice age. The water has risen. Most of that is continental land that's underneath the Sunda Sea. And so, again, this has happened somewhat recently, but still not a great example. Technically, seas like the Black Sea, Caspian Sea are Epiric seas. They're fully closed basins, so they don't really have a great interconnection with the actual water bodies outside of them.
What about the Mediterranean?
So the Mediterranean, I'm glad you brought that up. So I was just about to say the Mediterranean. So the problem with the Mediterranean's got a true ocean basin. the Mediterranean has been actually formed by tectonic processes, essentially by back arc spreading of the rotation of Italy. So after it slammed and created the Alps, it's rotated and moved out. And as it's done so, it's created the Mediterranean basin. So the Mediterranean basin, in this core of the Mediterranean basin, has a proper deep ocean. It has a proper abyssal plain. So it's not a true Pyrrhic sea. Okay, isolated platforms, all right? One of our final ones. Again, so we've talked about kind of this, I haven't talked about the scale too much. Again, a lot of these are kind of in the scale of 10 to 100 kilometers wide, all right? And in the Pyrrhic platforms, we have huge scale, okay? From 100 to 100,000 kilometers in width. But the isolated platforms are usually relatively small. They can be as small as half kilometer, kilometer, and maybe up to hundreds of kilometers, as we'll see in a second here. Okay, so they're 10 to 100 kilometers wide. They're commonly, very commonly located offshore from shallow continental shelves. Again, as you have sea level rise, these things tend to form in the distal parts of that continental shelf. And they're typically free of clastic sediment. Why are they typically free of clastic sediment? Why do we not have a lot of clastic, siliciclastic deposition in an isolated platform? Because they're isolated, right? But they're not made of volcanoes and so on and stuff like that. You have volcanoes that can form around them, like atolls and so on. When we talk about a proper isolated platform, a proper fully carbonate platform, it's all made of carbonate. The whole thing is carbonate. So there's just no siliciclastic rock for it to rework and to deposit. So there may be rivers and stuff like that. There's still going to be creeks and little small rivers and stuff like that. But it's not going to be moving any siliciclastic or clastic sediment. Obviously, the best example of this is the Bahamas. All right. So in the Bahamas, you have a front kind of reef. And the one thing we've talked about that exists a lot in the Bahamas is behind the front of these reefs, you have these big ooid shoals. These huge, essentially, actually don't want to show the next slide just yet, but these big ooid shoals. Based off that image, what direction is the current heading? Just say a directional orientation. What do you guys think? To the west. Yep, exactly. To the west. Okay, this is essentially taking these big sand waves, if you will. You can kind of see that we talked about this image before. These big ooid shoals that are pushed off of that front of the reef, and you can see all the detritus that's being created along the front, along that fringe reef. Okay, is being pushed off to the back in these giant shoals of essentially ooids. Okay, again, those ooids, those concentric rings of calcified sediment that just kind of build up layer after layer as they roll. So these ooid shoals of the Bahamas are essentially a relatively big player across a handful of platforms around the world, but not nearly as prominent as what you'd find along the edge of continents. And one thing I kind of missed to say here is, you see the location of the Bahamas? We're still just off the continental shelf of the United States, of Florida. Okay? So these aren't just forming out in the middle of the open ocean. Usually, these are something that's associated with the edge of some kind of continental platform. And we'll talk about that in a second of why that is, essentially why they're essentially near some kind of continent commonly. So, again, going back to what forms these carbonate environments and what affects these carbonate environments. So, water quality has a big influence on whether or not you're allowed to build a reef. So waves oxygenate the water. If you think about things like sponges or porifera, all right, and corals, they need water, and bryozoans and many other organisms, they need water to be pulled through them. They're not swimming around. They're sessile, essentially filter feeders. They sit in one place and they just allow the currents in the water or the waves to push organisms through them. Okay, so waves are essentially almost a necessity for coral reefs because a lot of these organisms need water to be transported across them or through them. And also, we're going to break apart organisms. This is what creates our wax stones and our pack stones. Instead of we just have pure bound stones. All right, we would just have essentially reefs that build up and get preserved in the geologic record. For the most part, you need to actually crush these things down to create a lot of the rocks that are preserved. And obviously these transport sediment. So currents, they move cold, warm water along a coastline. Again, this can bring nutrient-rich waters. As, again, Tessa Hill brought up, this is along the west coast of North America. This is essentially temperature in degrees Celsius. We see the coldest water is located just off the coast of California. That is because big currents bring water down along the west coast of North America, and that essentially moving water out of the system. It has to replenish that water, so it brings it up from the deep ocean and brings it up next to the shoreline. Now, as she talked about as well, this is very rich in CO2. These are a little bit anoxic waters because they're deeper. They're not in an area that's been oxygenated by waves. Okay, so this can affect the chemistry. This can affect also what type of organisms can live there. Okay, if organisms struggle with that slightly anoxic waters, then they won't essentially exist there. Just to show you how strong these currents can get, I just wanted to show a quick video. It's relatively cool. If it opens. There we go. Okay, I'm going to skip the sound because it's very like fluffy sound, and I'm going to kind of skip ahead. But this is in the four reef environment. So this is just in front of the actual reef. Sorry, camera. I'm going to turn this light off really quick. These things move a lot of water. You see that in that four reef environment too. You don't have the big coral buildups. A lot of this is just kind of little algal blooms or filter feeders. Maybe some kind of maybe some sponges or porifera might be out there. But for a lot of the organisms, you're going to see maybe some bryozoans or other kind of filter feeders that are taking advantage of these currents. Without these currents, there would not be plant life there. Okay, the currents are moving those organisms through, moving that water and other little forams and other little organisms that they chew on through that water column. So, yeah. I don't know why I jumped ahead so much there, but. Okay, turn this back on. So I want to save a little bit of time at the end here, but we should be okay. So again, without waves, without ocean currents, again, a lot of organisms aren't going to be very happy because they don't have the proper oxygen content or nutrients being passed through them. All right, so clastic sedimentation was another one of the factors that go into whether or not carbonate organisms can exist. First off, if you have a big plume of clastic sediment, like muds and silts and sands, coming out into an ocean basin, that is going to heavily restrict light within the water column. Okay? You put a lot of sand and silt into it, you essentially can't see. All right? If you can't see once you're down to 30 feet, you essentially aren't getting very much light and no photosynthesis. Okay, so whenever we have a lot of plastic sediment being dumped into an ocean basin, there is not going to be a lot of especially coral buildup. Another thing that it does is when you have sedimentation, so in this case, this is a picture of essentially an area where you've had heavy deforestation, upland of it, and essentially a lot of sediment has been now carried. Now, where there once was a reef, now a lot of sediment is being transported down that river system and out into the ocean, and it blankets those corals. And if you get a bunch of sediment on top of the corals and on top of those bryozoans and so on, they can't utilize photosynthesis and they shut down. So in modern reefs, so this is the northeast coast of Australia, and as you might have guessed, we are going to look at the Great Barrier Reef. So in biologic production here, essentially we'll look at this outer part of the reef and what organisms might be there. And commonly we think of these reefs as coral reefs, right? We almost just call reefs. When you say a reef, you usually call it a coral reef, okay? But corals aren't the only organism that are there. As we've talked about, all of these other organisms make a big impact on that reef environment. We've talked about most of these. We've talked a little bit less about green algae and red algae, essentially that encrust a lot of these corals, or essentially have a symbiotic relationship with some of the corals. But things like sponges, the porphyras, right, that are allowing water to come in through them and filter through them. The bryozoans are also filter feeders. All of the clams and essentially ammonites and all those different type of organisms that are essentially walking around the reef create a lot of biological material. And of course, those tiny little things, the foraminifera, are relatively prevalent there as well. So around the world, the International Ocean Drilling Program essentially goes around, and one of these, this site that we actually are just looking at here, has been drilled by the IODP just off Cookstown. And this will kind of get into sea level rise, but what you'll see here is that these different facies that we're seeing here essentially are all going to, just like in a siliciclastic environment, they're going to stack up on top of one another. Okay, because these margins are going to prograde out or retrograde back with sea level rise and fall. Now it's a little bit different mechanism compared to just straight sea level rise and fall. Okay, but in this location, essentially, you'll kind of have the corals are making up the bulk of the front of the reef, and as you get back, the red algae, and then more kind of muds and sands and wax stones and pack stones. The same concept in the past. They just see that this repeats itself at 170,000 years and again at about 85 to 20,000 years. But essentially, these exact same stacking patterns have essentially happened on top of each other during two big periods of sea level rise. I just wanted to bring this up because we talked, as I looked at this image, we've talked a lot about this in the past, okay, during siliciclastic environments. Talk with your neighbor about what the process is that's affecting the depositional environment at number 1 and number 2. Think about the geometry of the deposit. Okay? Think about what that deposit is in relation to the shoreline. So what process, what environmental process is happening here with all of these and here with all of these? What's the dominant process? Just think about it for a second.
Yeah, it's like
We talked about this a lot in shorelines, and there are a couple of major processes that affect shorelines. To win. What is the orientation? All right, I'm going to help you a little bit. What is the orientation of this compared to the shoreline? What are these? Parallel to the shoreline. What process dominates when we have essentially bed forms or land forms that are parallel to the coastline? What process dominates? Of those processes we talked about during coastlines, there's 3 big processes that are acting on coastlines. If you have things that are parallel to the coastline, what process is dominant? Yes, waves. Waves, okay? So you see how all of these reefs are essentially oriented parallel to the coastline? They're getting smashed back by waves, okay? So the dominant process acting on the outer part of the Great Barrier Reef is primarily wave action, okay? As you get farther inland, what is the orientation of all of these? And number 2? Perpendicular to the shoreline, okay? When we saw perpendicular bed forms and sand bodies in a coastline, what process was dominant along that coastline? Tidal influence, okay? Tidal influence. So again, these things are going to kind of create essentially different reef structure, and also different organisms are going to live there, okay? As you're out here, again, a lot of the stuff that can hang on and withhold some kind of battering by waves. So again, we talked about corals like to be essentially built out of things like aragonite, because aragonite has got a little bit of a sturdier structure to it. Okay, so those organisms that can handle that pummeling by waves are going to essentially be in those outer reefs. As you get farther back, these organisms don't have to deal with that that battering as much. They still have tidal inlets that are essentially coming in and affecting them, but a lot of that is just that water moving in and out on a day-to-day basis. A little bit less oxygen in the region, but slightly different organisms, okay? So again, along this coast, what I kind of was talking about with the IOD program was how these reef systems and how these reef tracts respond to sea level rise and fall. Okay, there are a bunch of different ones on here, but I want to just talk about essentially. Oh, I should put that wrong. Let's just talk about keep up and drowned. Okay, so give up, keep up, and essentially catch up is what I meant to say there. Okay, so give up or drowned are essentially the same thing. Sorry about that. I just made this slide late. But essentially, give up or drown means that sea level rises so fast that it can't actually keep up. Its rate of production can't keep up with the sea level rise. Sea level gets too far above it, and it drowns. It dies because sea level got out of reach. It got above that 100 meters, if you will. It got above that 80 meters. It got above that 30 meters for whatever organisms were there in that place at that time. And essentially, it was not able to survive. So this will commonly happen. You'll see these reef buildups that are just filled by sedimentation over the top of them because they were not able to keep up with that environment, okay? So keep up is kind of part of all of this. Essentially, there's backstep and catch up here as well. But backstep essentially is that sea level used to be out here. It's on more of a ramps type platform instead of like a fringed reef. And now you're building that reef again farther back, or you're building that carbonate platform farther back as sea level rose. Okay, this is more common in kind of like a ramp style or a rimmed or not a non-rimmed shelf. Okay, but keep up is the main one, I guess, and that's just saying that organisms were allowed to keep up with the actual sea level rise. They were able to build fast enough. They can, again, in that carbonate production in that upper 10 meters can be extremely fast. And they actually keep up with sea level rise. That was a big sea level rise at the end of the last ice age. All of the atolls in the world, we owe all of those atolls, those beautiful Bora Bora, the image I showed at the beginning of the last lecture. We owe all of that to essentially organisms being able to build fast enough to keep up with 100 meters of sea level rise. Okay, so almost all of the atolls in the world are part product of subsidence, but part product of essentially those organisms being able to keep up with a relatively rapid sea level rise. So yeah, ignore give up. Give up and drown are essentially the two same things. So a couple more environments that we're just going to touch on before we move on. Deep water deposition. So in the marine realm, we focus primarily on that near shore environment. But don't forget that deep water deposition plays a relatively large role as well. You have a lot of those foraminifera floating around, so those benthic or planktonic foraminifera. Some of them are siliceous, right? So some of them are built out of silica, and some of them are built out of carbonate. Okay, we've seen this image before, but if you look at a distribution, this is from your book, this is from Boggs. If you look at the distribution of these carbonate oozes throughout the world, anybody notice? So this is the pattern for carbonates. Okay, the calcareous oozes, if you will. Okay, the calcareous oozes. Anybody notice the pattern of what these things might be following?
Mid-ocean ridges.
Mid-ocean ridges. Okay, what is at a mid-ocean ridge that might actually help promote carbonate production where an otherwise relatively low nutrient, relatively anoxic environment?
Vents.
Yeah, black smokers and vents. Okay, oops, that's the wrong image. Put the wrong image in there. So essentially black smokers and vents. Okay. So those things will essentially give nutrients to the water column. Now the last part of this, again part of this learning program that we're involved with, is that we do a little more active learning. I wanted to just do my class like I mostly do it, where we do a Socrative quiz at the beginning, a Socrative quiz in the middle. We do a little bit of discussion in between, essentially pair up and group discussion. But we're going to try another method here. So row one, okay? What we're going to do is we're going to split in half, so this half, and then we're going to split up by rows, okay? And what I want you guys to essentially determine is in your small groups, okay? Number one, row one, you guys are the outer shelf and the slope. Okay? You guys are this environment. Number 2, you guys are, row 2, you guys are the reef environment. Okay? Number 3, you are the back reef. Okay? So this environment right here, and the essentially inner shelf, so the lagoon environment. Okay? And then lastly, group 4, you guys are, it's kind of depicted a little bit wrong here, but you're the tidal flats, if you will. You're the tidal flats in the foreshore. Okay? Now we are focusing this on a rimmed shelf environment. Okay? So not an open environment. This is a rimmed shelf environment. So think of South Florida Bay and think of that type of environment. Okay? Now the left side, you are going to focus on processes. Okay? So what is affecting your environment? Think of the waves, the tides, the currents. Okay? What is actually affecting your environment? You're going to focus on, do you think there would be any sedimentary structures involved? Okay? And what type of matrix might be surrounding your fragments? Okay? What percent of mud and matrix do you think will kind of be in your environments? Again, some of you kind of have 2 environments. Again, outer shelf and slope. You guys could talk about what's happening at the end of the slope a little bit as well. The reef, I really want you guys to focus just on reef. Inner shelf, again, you guys kind of have this environment that's right behind the back reef, okay? But you also have what's happening in the core of the lagoon. And then tidal flats, you guys are also considering what might be happening just along the shoreline. For the most part, you're thinking about the tidal flat region, okay? Now on the right side of the room, you guys, I want you to think about what organisms would be present, okay? What are essentially the organisms that you'll find there, and think about what that then becomes as far as a sedimentary deposit. So I want you to think about, remember the term allochems? So both the skeletal and the non-skeletal allochems that you might find in this environment. Now for the first 2 to 3 minutes, I want you to work on this without internet or phone resources. Okay? So for a few minutes here, I want you guys to talk about this, make a list, again, start to actually write these things out. I can write some of this stuff on the board too, so it'll help you actually figure out what you're supposed to go after. But for the first couple of minutes, I want you just to think about this without using any kind of internet or phone resources. Okay? Go ahead. I'll write some of this stuff up on the board here too.
Is it your right or our right?
Oh, sorry, my right. My right. This side is the right side is the organisms and allochems.
Oh.
My bad. My bad. I guess you guys are thinking facing me. This side of the class, think of organisms and allochems. This side, think of process, set structures, matrix. Okay. Clarity.
What's the reef, bro?
No, we're on the face.
No, we're both. Oh, no, never mind.
Yeah, we're on the face.
When he's talking to us, he's talking about the reef too. No, there's not much shit there at all.
Yeah, that's what I'm saying. Like, there'd be like, what, like, detritus from the reef, like, coral fragments, like...
Plankton, I think
You also are free to ask me questions during this part of it. I kind of want you guys to struggle with this for a second, and then you can start to use the internet.
Yeah.
The lagoon. So lagoon is typically like flat. It can get down to 30 or 40 meters.
Is that all we have to answer? Everything else, there's just so much more.
Right now, just think about.
Would you say, would it be
Okay.
Reflectance of political.
And because we're going to run out of time, I actually am going to go ahead and say, go ahead. You can use any internet or online resources, or look through your notes, your books as well. But you can use other resources to try to figure out what organisms or what structures might be in this environment.
Skeletons.
Yeah.
Yeah. Skeletons. Non-skeletal.
I mean, there is no skeletons.
See what might be down there. Well, that was all up.
So you'll have about 2 minutes to do this part of it. You be struggling? Yeah. Yep. Okay. So what?
Get your Google machine out.
Yeah.
They're all over the place.
It's also free. Oh yeah. Yeah.
Yeah, but you get like that's the size. Yeah, you get essentially you still call it limestone. So siltstone, like what we're trying to imagine here is like so essentially in this environment, a lot of the down there, you don't use like 2 seconds. I'll come back to this in a second. I'm gonna switch over to here. Okay, now what I want you to do, instead of meeting with the other group in your group, I want you guys turn to this group and talk about what your results are. Okay, so you guys are turning to the group behind you and tell them about what your results are. Same, they're going to tell you as well. Same with you guys. You guys go to the group behind you and talk about what organisms. Okay, so I want you to stay within your left and right. So you're talking about process on this side, my left, and organisms on my right. You're allowed to change what you think of too. Think about the organisms that are going to like be preserved or create something as well. What are your allocams going to be in the end? Sorry. We have high wave
I just never tried that one. The only one I've had is the one I just use on work.
Yeah, yeah. Yep. Oh, we're already on that, huh?
Have you tried?
I have not. I'm good. Keep on topic for a little bit here, though. Only 5 more minutes.
Maybe you guys got trigonauts too.
Okay.
Also related to reefs.
Has everybody had a chance to kind of talk about organisms? Hopefully it's made you think about a little bit what's different in the area surrounding your environment. Now come back together and now meet up with the other half of your row. And I want you guys at this point to tell me what rocks will be preserved. Okay? So I want you to use the Dunham classification. Okay? So the Dunham classification. So if you can just think of the grains and the grain size and the matrix, that's one thing. But the other element of this is because we talked about the biology and what organisms are present, what organisms might be present, I want you to also add some nomenclature to that. Okay, so is it just a waxstone, or are you going to have maybe a bryozoan waxstone or a oolite or something like that? So think of the non-skeletal fragments as well. This might be a little bit harder because we didn't go into really big detail about essentially what organisms are in each one of these environments as far as where do echinoderms exist, where do crinoids exist, but give it a shot, okay? Give it a shot. So talk about waxstone, packstone, grainstone, boundstone, all that, but then also talk about what defining organisms might also be creating your rock, okay? So using the Dunham classification.
Well, the only really organisms that we have are planktonic and bentonic.
And then I'm going to keep you for 1 extra minute just so we can all say what we think.
So it's not really going to be very much like what it's like a lot of organisms that pick up a rock. It's going to have like a planktonic mudstone.
Like at the very bottom, maybe?
Did you guys know?
So, if you want to show your diagram.
Pretty good, yeah.
It's just like planktonic and then the benthic allochens, where you like much outside of there, like on the big drop off.
Once you get down out there, not as much. All of that reef material is getting broken up and transported.
We thought coral fragments would be there too. So that could like add to like the deposition.
Okay, because I don't want to keep you too long, what I'm going to do now is just have somebody from your group, we're going to quickly say, all right, what type of rock or what type of deposit in the Dunham classifications would you guys think you guys would find? Essentially, again, in their environment, it is the 4 reef environment and the slope, okay? What are you guys going to have?
Packstone?
So you'll have a lot of packstones. Yep, exactly, because you have not the fully energy environment, but what kind of organisms were you part of that packstone?
Coral fragments, but then
Coral fragments, bryozoan, all those fragments that you would have up here. Okay, all those fragments that are essentially building the reef, they're also going to be out here. And the reason you're going to have a packstone and not a grainstone is because you are getting far enough off the water column where you're probably getting some suspension settling of mud, right? How about as we get farther out? More in the micrite, waxstone type environment. Okay? All right, go ahead.
We got mainly boundstones
Yes.
and grainstones.
Yep, exactly. And then what type of organisms? The whole suite.
Everything.
Yeah,
Like
exactly.
bryozoans,
Yep.
corals, sponges.
Yep. Is there anything you would not find a lot of there?
Probably algae, since the
So yes, exactly. So a lot of the non-skeletal fragments aren't going to be there. Okay, so as far as your organisms and your allochems, most of the actual fragments are going to be essentially of that reef complex, and you're not going to have a lot of muds or pelloids or grapestones or any of those other non-skeletal things. Row 3. What do you guys think?
So we said probably more like paxone or waxstone.
Yep.
So like some sand, but also maybe a little bit of mud.
Okay. So where else did we say some sat a little bit of mud? Right? In the 4 reef environment. These are going to be very similar They are both made from essentially waves crashing through this environment. Out here, it's going to be a little bit more complete fragments. As you get farther in, these are constantly still getting swashed around, so the grain size might be a little bit smaller and a little bit more sorted, if you will. Okay, so a little bit less sorting out here. Organisms?
Fish and also some bivalves.
Yep, and then what non-skeletal fragment are you going to start finding in your lagoon? Pelloids, and stuff like that. Okay, in the lagoon environment, you'll have a lot more of the pelloids and stuff like that, so wax stuff. And last, back row. Sorry, taking you over. Sir.
So let's see, mudstones.
Yep, mudstone naming. What's the name of mudstone? Nick. Yep, Nick right. Yep. Just because that's the only one that's outside of the Then, what are non-skeletal flats? What you guys find? We talked about in those tidal flats. What are those chunks called? Those chunks of non-skeletal fragments called. They're ripped up in the environment. Interclast. Yeah, interclast. Okay, so you're going to find a lot of interclasts. How about organisms? What kind of organisms are going to live up there? Do you find anything online at least? So some worms, some bioturbation. Also things like mollusks. Okay, a lot of mollusks, crabs, stuff like that. Okay, I've kept you guys long enough. Go ahead.